right, let's go ahead and run through Webwork 4. So x sub t is the value of a measurement at time t. Match the long-term behavior of x sub t to the corresponding cobweb diagram. All right, so I'm going to make another video talking about cobwebs in detail. So for this, I'm going to go over what the answers are and very briefly talk about why, but for more in-depth stuff, find another video. Okay, so if we look at what's happening in slide 1, the red, you know what, I got the way to do colors, so let's just do that really quick. Change this size, great. So this red line coming from the origin, that's the line y equals x, and it's very important for cobwebbing, whereas the black line, which looks something like this, that is the graph of our updating function. Okay, so that's the thing that looks like x sub t plus 1 is equal to, and based on this graph, it's going to have some slope and then x sub t plus and then some like y-intercept. Okay, I can make this plus b, whatever. So mx plus b. And we also know that m is something less than 1 because this line has slope 1 and it's more steep than the black line. But whatever. Okay, so that cobweb looks like this. Boom, 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 and it just kind of keeps on going. So what's happening is if this is x0, then this y value is x1. So this has a y value of x1 because when you read an updating function, the x subscript t is your input and the x subscript t plus 1 is your output. So this axis is the x sub t plus 1 axis, and this axis is the x sub t. So if I feed in x subscript 0, then the output, which is the y value, is going to be x subscript 0 plus 1, aka just 1. So the output is x sub 1, and that's what this is saying. And then the reason we travel horizontally is because we go to the line y equals x. So this y value used to be x1, and now this spot right here is x1, x1, okay, oops, which is just saying like this value here is x1. So traveling to the line y equals x is a way that we transform what used to be a y value into an x value, and that's nice because if I were to plug x1 into my updating function and then hit my updating function right here, then, so actually, hold on, let me, here was x1, here's x2. So on my updating function, my y values correspond to the next measurement. So if I plug in x1 as an x value, the y value is the next measurement, which is called x2. And so then that happens and happens. So anyway, what's happening is the measurements are decreasing towards equilibrium. T starts large and decreases heading towards equilibrium, so that's a B. Boom. All right, great. All right, so now speeding up a little bit, if I just look at the graph for number 2, you can see we head towards equilibrium and we're increasing. The y values from every time we hit the black line are a little bit higher. Okay, whereas in number 1, this is number 1, the y values every time we hit the black line are a little bit lower and they're traveling towards equilibrium. So anyway, for number 2, the value is increasing and heading towards equilibrium. I would say D, okay? And you might ask yourself, why did it not say C, the value xt grows at a constant rate of change? Well, for starters, it's not growing at a constant rate of change. Let's graph this really quickly. In fact, well, maybe I can just, so we want to look at the change in y values from every time we hit the black line. Okay, so the black line looks like this, and there's this line, boom, and now if I was to cobweb, I come up, boom. Okay, so here's x1 when I start at x0, and the fact that this red line is the line y equals x means if you know a y value, then you also know the x value, and so this is also x1. But okay, so we can avoid finding it on the x-axis by doing the cobweb trick. I hit this point, and now I know this is x1. I go up, and I hit my updating function, and so this is x2. And I can also say this was x0. Okay, so notice the jump from x0 to x1 versus the jump from x1 to x2. That's not the same size. This is not a constant jump. And it gets even worse. x3 is like right there. I'd have to zoom in to start to be more accurate, right? And it gets worse and worse and worse. Bop, 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 bop. You know, the vertical jump, so then this is x4, and then this is x5. They're really bunching up because they're getting stuck at this equilibrium value. This is not a constant rate of change. So C does not apply here. Okay, in fact, let's just say that this is what C would look like. Okay, if you look at the Y values from every time that we hit, go away, great. The Y values from every time we hit the updating function, there is a constant rate of change. So this is this, and then we have this, and then we have a parallel line. Whoop. And now, wherever I start, let's say this is x0, I go up, I hit, I go up. So here was x1, here is x0, here is x2. Okay, that doesn't look so constant because of my artwork, but let's be a little bit more careful here. I can get this a little bit higher, it doesn't really matter, but boom, boom, here's x3, boom, boom, here's x4. And if I really drew this to scale, all these gaps would be the same size. Okay, constant rate of change in our x measurements. Okay, so that leaves 3 to be the one that oscillates. Look at where, so if you keep track of your blue line, starting on the x-axis, I guess, oh, that'd be a faster way to do this. I could just sort of copy image, hop over here, and paste the image, if my eraser would work. You know what? I wonder if I just... okay, just don't care. Whatever. Keep track of this blue line. It starts on the x-axis. It goes up. Okay, now, every time it hits the black line that's sloped, the y value goes from something high to something low. Back to something high, back to something low. High, low. High, low. High, low, right? So anyway, that's the oscillating behavior. But I said I wasn't going to go too much into it. So, oops, previous problem. I never hit submit. Oh, and I have to run back through this. Okay, this one was decreasing. You know what? Yeah, whatever. They're right. Okay, let's look at this one. Consider the updating function graph below, the cobweb diagram, read off the values of cobweb filling and blah, blah, blah. Okay, B0, this is where you start on the x-axis, and that looks like it's at 2. Because it's, you know, one more block to the right from 1. Okay, B1, so we're trying to read, all right, let's try this, copy image, paste, great. Okay, so here was B0, this spot, because it lies on my updating function, has coordinates B0, B1. Because my updating function, which is this black curve here, right, that is some kind of function which will tell you b sub t plus 1, and it's some kind of function of b sub t. So if I plug in b sub 0 and I apply that function, I'll get b sub 1. So if I plug in b0 and I apply that function, I'll get b sub 1. Okay, so then this is b sub 1, and let's see, this is 2, 3, 4, 5, 6, and a little bit. All right, so we'll just say like 6 1/4 or something. I don't know, I'll just say 6.3. I bet it'll accept it. All right, so now we follow the spiral. Here's the line y equals x. And so what that does, so a horizontal movement keeps the y value the same. So this point here has a y value of b1, and because this is the line y equals x, that means the x value is b1. I don't know if my dog's groans pick up on the mic, but whatever. Okay, so it's a way that we can now get x to be b1. So that means this input here is b1. And what is f of b1 going to tell us? It's going to tell us b2. So this spot right here, the y value is b2. And that looks like it's about 4.5. Let's run with it. Sure. All right, I'm going to speed it up a bit. So now this y value is b3, and that's maybe like a 5.2. And this y value is a b4, and that's maybe like a 4.8. And this y value is a b5. We're getting really close to 5. Maybe it's like, I don't know, 5.1. We'll just go with that. And what does it look like is the equilibrium value. That's when these two lines intersect. And that looks like it's hitting at 5. Right, 2, 3, 4, 5. And it'll always be the same y value as it is x value. An equilibrium is the special number where if you plug it into your updating function, you get the same number out. It's the special spots where b sub t plus 1 is going to equal b sub t. Okay, which graph shows the solution function? So if you look at what's happening with these y values, so the solution function, so now our x-axis is t and our y-axis is bt. This is for a solution function. Whereas up here, our x-axis is b sub t and our y-axis is b sub t plus 1. This is for an updating function. Okay, so anyway, in the solution function, what happens? Well, at t equals 0, b sub 0 was 2. So I'll make this 2. Okay, and I'm looking at the columns I'd entered. So then what's b sub 1? It was 6.3. So if this is 1, then, okay, I shouldn't put 2 there. That's too high for what I want to graph. Maybe I'll put 2 here, and then up here was 6.3. So at 1, we're up at 6.3. And then we go down to 4.5, and then we go up to 5.2, and you get this kind of like oscillating, and it mellows out at 5. Okay. So A looks pretty good, although I'm not counting anything. D also looks pretty good, so now I might have to count, but I kind of don't want to, so I'm thinking we just try A, and if it doesn't work, go for D. When I say you have to count, I'm just checking if B1 is roughly 6.3. So if I look here and I count in the spot 1, I'll just do it. 1, 2, 3, 4, 5, 6. Yeah, so I think it's A. Okay, great. Let's submit. And yeah, it was. Okay, next. Small, let's make it big. I wonder why it pops back up like that. All right, find the equilibrium value. Okay, so the equilibrium value is the special number where if you plug it in for b sub t, then it'll end up also being b sub t plus 1. Okay, now this is not the right way to say it mathematically. Mathematically, we say it like this. So here I am plugging this in to my updating function, and then it is also the output. Okay, so the function essentially doesn't do anything, even though it looks like it does. So, and this is telling you how to solve for it. So if we look at the first one, the updating function is b sub t plus 1 is equal to 2.5 b sub t. Okay, and our goal is to solve an equation that looks like this. So just get rid of the subscripts. So you have b is equal to 2.5b. Now, if I want it to exactly match what I highlighted it in orange, then the name is b star, and so I should call it b star. But you see on this side, on the right-hand side, we have f of b star. I've applied my function to b star. What does my function do? It multiplies by 2.5. And on the left-hand side, I just put down b star. And see, this is why if you just get rid of subscripts, it works. Like, you don't need to write a star. Just don't write subscripts, and it's the same idea. Okay, so let's go ahead and solve for b. So this is where you have to be careful. So careful, okay, exclamation point. B could equal 0, right? Notice if you plug in 0, you get the equation 0 equals 0. That's true. That means you found a solution. But the reason for me saying be careful is because a lot of students looking at this will understandably want to divide by b. Okay, but let's see what happens if you divide by b. Well, on the left-hand side, I divide by b. On the right-hand side, I divide by b. And on the left-hand side, b over b is 1. And on the right-hand side, I get 2.5. Look at what we just concluded. Oh my goodness, 1 is equal to 2.5. That's not true. How could we get that? Well, it's because we did a step that isn't valid, right? The highlighted equation implies the red equation only if you do valid logic. And you might think, but dividing by b, that's valid. Not if b is 0, okay? When you divide by a variable, you have to ask yourself, am I dividing by 0? And if so, well, you got to do something else. So what's the something else that we could do? We could subtract b. So then my left-hand side is b minus b, and my right-hand side is 2.5b minus b. Now what's this? This is 0 is equal to, and what's this? This is 1.5 copies of b. There's different ways to see this, but one way is if you factor out the b, right? If I sort of distribute that back in, I get here, and 2.5 minus 1 is 1.5. So now we're here, and we ask ourselves, what number do I have to multiply 1.5 by to get 0? And the answer is 0. So anyway, the equilibrium value here is 0. Cool. All right, I'm not going to do all of these. I'm probably just going to do one more, because once you can, it's literally just get rid of the subscript. M is equal to 2m minus 4, and solve for m. That's it. That's what you do every time, okay? All right, so what should I do? Let's go ahead and subtract m from both sides. So now I have a 0 over here, and I have m minus 4. And maybe you can already just see that m is going to be 4, but if you can't see it, then, or if it's not so obvious, I should say, then add 4 to both sides, and then you get the equation m equals 4, okay? So here we have 4. And notice, if you, okay, why was that? Oh, there we go, 4, great. Notice, if you plug 4 in, then you'll have 8 minus 4, you'll get 4 out. If you plug 4 in, you'll get 4 out. That's an equilibrium. It's when the updating function essentially doesn't change anything, okay? All right, so I'll hit submit. You can see, yes, indeed, you just have to solve for when the left and right-hand sides are equal. You get rid of subscripts. That's the process, okay? All right, so now we have an updating function graphed in red, and then the y equals x line is blue dotted, and I say y equals x, but it really is this, and that's called an equilibrium line. It's when what you put in is the same as what you get out. It's when your measurement at time t is the same as your measurement at time t plus 1. It's when the population this year is the same as population next year. It's when things have equilibrated, you know what I'm saying, equilibrized, equilibrated, whatever. All right, select one or multiple appropriate statements from the list. Okay, so 8, 8 is stable. That's not true. Okay, so how do I know it's not true? It's because the slope of the red line is steeper than the slope of the blue line, but let's see why that matters. Boom, boom. Wait, this is silly. Did I not learn my lesson the first time? No, the answer is no, I didn't. Go away, let's get rid of this, and paste. Great. Great. Cool. So what we should do is cobweb, okay? So so 8, here's 8. Stop it. Thank you. Here's 8. So I start a little bit to the right, and I go up, and I hit updating function, and then y equals x. Updating function, y equals x. Updating function, y equals x. And see what's happening? I'm going away from this spot. So this point here is not stable. The same thing would happen if you started on the left. You do updating function, y equals x. 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 And you see I'm marching away. Okay? Cool. All right. So that's not stable. A similar analysis would actually show that this line, or sorry, not this line, this intersection is stable, and it's because the slope of the red line is less than 1. But it's actually, at this point in time in the course, it's because the cobweb brings us there. It brings us there on the left, it brings us there on the right, right? We're marching towards that spot. So that's a stable equilibrium. Cool. So let's see. 2, 2 is stable, and that's all I can say, right? Because 8, 8 is unstable. So let's submit that. There we go. Next. All right, the lung model. Oh, the lung model. Yeah. Cool. Boom. All right. So this one I also need to, if you look at my old playlist, there's a lung model video for like 2022 or 2023. I can't remember. Anyway, here's the deal. You got some lungs. All right. Boom. Boom. And they hold 2 liters. All right, sweet. That's how much air these lungs hold. This is definitely an adolescent child because an adult lung is about 5 to 6 liters. All right, W is the tidal volume, which is to say that, I don't know how to draw a face. Okay, when you breathe air, you don't fully collapse your lung. That would be called a collapsed lung, and that is lethal. You leave a certain amount of air in your lungs. So what they're saying is the volume that you exhale is the same as the volume that you inhale, right? You're going to re-up whatever you exhaled, and that volume is 0.5 liters. This is called the tidal volume, whatever. Okay, what counts as one breath? Well, the way we're going to do it is we're going to begin with an exhale. So one breath is an exhale followed by an inhale. Okay? All right. So, cool. Now, C subscript T is going to be the concentration in the lungs at time T. Not time T, at breath T. Okay, so C sub 1 means you take one breath. Exhale, inhale, that's one breath. There's some new chemical concentration in your lungs. Okay, so we got all that going. Now, this wonderfully drawn person is sitting in a room, and there's some particles in the air in this room. Okay, and there's some concentration, and that's gamma, and that is 4 millimoles per liter of this mystery particle. Okay, now there's also particles in the lungs, and the concentration in the lungs might be different than the concentration in the room. Maybe you're just outside and then you walk inside the room, right? So the concentration in the lungs is called C sub T. When you first walk in the room and you've taken 0 breaths, the concentration at 0 breaths is called C sub 0, and for this problem, with what's given to me, is 1 millimole per liter. So let's figure out the concentration after 1 breath. We're going to figure out C subscript 1, okay? So here's the plan of attack. C sub 1, and this is a concentration, which means we have to pay attention. No, it means the units are millimoles per liters. So that's stuff over volume, okay? So here's the plan. Let's figure out the stuff and divide it by the volume. Okay, so what are we going to do? Well, how much, so I'm looking at step 1 on the Webwork, the amount of chemical in the lungs before breathing. And notice this says amount. Okay, so instead of me writing the word stuff and being playful, let's use the words that show up in the problem. Okay, so millimoles are measuring the amount of something. So when the word amount shows up, they are talking about just millimoles. They are not talking about concentration, right? Concentration is the ratio of millimoles to liters. Amount is just the millimoles. So how much amount do we start with in our lungs? Well, every liter of my lungs contributes 1 millimole, and my lungs have 2 liters. So if I multiply the volume with the concentration, I'll get the amount, right? So I would do 2 times 1. I'm doing 2 times 1, and this 1 is C0, and this 2 is the lung volume, okay? So I begin with 2 millimoles of substance in my lungs, okay? And then I'm going to take a breath. And what's a breath? It's an exhale followed by an inhale, okay? So when I exhale, I'm getting rid of stuff. I'm taking away stuff in my lungs. All right, how much do I exhale? And when I say how much, I mean what amount, how many millimoles? Well, what I know about my exhale is that its volume is 1/2 liter. Oh, and I also know the air of that exhale is coming from my lungs. So that means the concentration of the source is my C sub 0 in this case, because no breaths have happened yet. So if I do 0.5 times 1 millimole, when I exhale my 1/2 liter, I exhale We'll continue to sort of like times 1, okay? This is still C0, and this was my tidal volume. That's the volume that you exhale and inhale, okay? Okay, that may have been confusing when I say and. It's the volume you exhale, which is the same as the volume you inhale. So I had 2 millimoles in my lungs. I exhaled a half a millimole. Now I'm going to inhale. Okay, so now I'm going to add to the amount of stuff in my lungs. I'm going to inhale a half a liter. That's also my tidal volume. But the air that I inhale is not the same as the air that I exhale. I exhale from my lungs. That's the source of that air. But I inhale from the room. Okay, so that's where gamma comes into play. And what was gamma? It was 4 millimoles, right? So here, this numerator is the amount of stuff that occurs during one breath. And I've actually just done like a lot of blanks, so let's catch up really quick. The amount of chemical in my lungs before breathing, 2. Where did that come from? That was actually 2 times 1, because 1 is my C sub 0. In general, this is C sub 0, okay? So your problem may vary. The amount of chemical that I breathe out, well, so in general, this is W times C sub 0, okay? It's the amount that you exhale in volume, right? So that's a half a liter for me, times the concentration of the air in your lungs, which in this case is 1, so I'm just going to leave it as 0.5. All right, the amount of chemical in the lungs after breathing out. Okay, well, first off, this has the word amount that appears in step 3, so we're talking about millimoles. So how much chemical is in the lungs after I exhaled? Well, it's the 2 I started with minus the 0.5 that I exhaled. Sorry, you can't see it. Okay, 2 minus 0.5. I guess I could have just... Could I? No, I can't. That's weird. Okay, can I collapse? It doesn't matter. It doesn't matter. All right. The amount of chemical I breathe in. So now I inhale a half a liter, but the source of that air has 4 millimoles per liter. The amount of chemical in the lungs after breathing in is equal to, well, the amount I started with minus the amount that I exhaled plus the amount that I inhaled. Okay. And now, the new concentration in the lungs, here's the amount of stuff. If I divide by the 5 liters of my lungs, I'll get the new concentration. So I need to move this over so I have room. So there's the amount of stuff divided by 5, submit. Why don't you like this? The concentration of chemical in the lungs after breathing is equal to, this should be correct. All right, let's remember I got 0.7. Okay. I'm divided by the wrong amount. I'm sorry. 5. Why did I divide by 5? Because I'm so used to saying adult lungs are about 5 liters. But for this problem, the liters in my lungs are 2 liters. Okay, now I was about to just say show correct answers and do it. But when I double checked, the thing that I saw, that I was like, wait a second, that doesn't make sense, is the concentration I started with in my lungs was 1 millimole per liter. I'm looking at that C subscript 0. It's 1 millimole per liter. The concentration of the air in the room is gamma. It's 4 millimoles per liter. It's higher than the concentration in my lungs. So when I do the gas exchange, when I exhale, inhale, and swap out air in my lungs for air in the room, the concentration should go up, right? I'm getting more chemical in my lung because there's more in the ambient air. So the fact that I went from 1 for C0 to 0.7 for C1, red alert. Okay, something's wrong. So indeed, I did have the wrong thing. I was dividing by too much. Now let's try it. That looks better. And you can see the concentration went up. It's up to 1.7. Okay, or 1.75, whatever. All right, so we're going to try and put all this in a table. So, all right, we have a lung volume of 4 liters, a tidal volume of a half liter. We begin with an initial concentration of 0.1. Okay, whatever. So before I exhale, how much chemical is in my lungs? Well, it's the amount of air in my lungs times the concentration. So I'm literally just doing second column times fourth column. And if you look at the units, right, the second column has units of liters. The fourth column has units of millimoles per liter. So if I multiply the 4 and the 0.1, the liters cancel, I get units of millimoles. Like, this is kind of trying to give you big hints and stare at you in the face. You could run through all of this without knowing any of what's happening and just run with the units, and you'll essentially get the right answer. Well, okay, I said that, and we get to this first blank where we should think a little. So after you exhale, how much volume is in your lungs? So I began with 4. I blew out 5 liters. What's left over? Oh, 3.5. No doubt, no doubt. Go away. Thank you. All right, and how much chemical is left in your lungs? Well, it's your concentration times the volume that's left. Okay, fine. Now I inhale, and I'm inhaling from the ambient room. And the ambient room has 0.18 millimoles per liter. This is 0.18 millimoles per liter. So see, these 0.1s are talking about the concentration in your lungs. This 0.18 is talking about the concentration in the room, okay? So subtle, sneaky, be careful. All right, so the half liter that I inhaled came from that concentration. So now we're going back to talking about in the lungs. See how this is like weird and subtle? It could be very sneaky and confusing. So in the lungs, I now am back up to 4 liters of air. All right, how much stuff is in my lungs now? Well, after I inhaled, there was this much stuff. Okay, so my lungs are not at full capacity. There's that much stuff. But then I inhale. I'm going to add volume to my lungs. And I add this half a liter that contains 0.18 for every liter. So this is the amount of stuff that's in my lungs after this breath. Okay, so now the new concentration is the new amount of stuff divided by the volume of my lungs. Okay, that's my new concentration. So my new concentration after one breath is that. Great, there it is. Boom. Next. All right, more ways to say the same thing. So let's get this to be bigger. Let's get this over here. Boom. You can guess, like when you're thinking, what should I know for a test and stuff, right? Well, look at how much there's lung model here. There's going to be a lung model question on the exam. There's got to be, right? But you can always check the sample midterm 1. It's up since the beginning of the class, and you can see, like, does this appear? If you're thinking, like, man, this is confusing, I hope it's not on the test. We've had like 5 questions of lung model by now, and maybe only 3 actually, but whatever. It seems like a significant amount, so that should be a big hint. All right, so here's what's going on. There is the volume of your lungs, which in this case is 3 liters. There's your tidal volume, how much you inhale and exhale. In this case, that's 0.4 liters. It turns out, if you work out all the algebra and blah, 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 well, no, let me just say, what we've been doing is that the concentration after taking another breath, this is concentration, which has units millimoles per liter, and this happens after another breath. Okay, so you have, right, that's why we have the t+1. So, well, there's like the amount that you started with before this, another breath. So how much do you start with? Well, that's V times CT. It's the volume, 3 liters, times whatever the original concentration in your lungs was. We've been going from C0 to figure out C1, but in general, there's some concentration. You take another breath, you have another concentration, okay? So I don't know what this number is, but I don't need to know, okay? I'm describing the process. What I need to know is that the units of this number are millimoles per liter, and the units of this number are liters. And goddamn, if I multiply them, the liters cancel, I have some amount of millimoles, okay, in my lungs when I first begin my breath, meaning I haven't inhaled or exhaled yet, okay? Really, I should say I haven't exhaled yet. So, V times C sub T. That's the amount that I start with, okay? Now, I exhale. How much do I exhale? Well, there's the volume that I exhale, but how much stuff do I exhale? How many millimoles do I exhale? Well, that's the volume that I exhale times the concentration of that air. And it's coming from my lungs, right? So the fact that the air is coming from my lungs means that these have the same source. They're describing the same air. It's the same concentration. Okay, now I inhale. Inhale. How much stuff do I inhale? Well, I inhale the volume W. Okay, we should keep track. Like, and what's its source? Its source is gamma. Okay, gamma is the ambient air, and of course, this problem changes notation. They're calling it beta. Okay, the beta equals 3 millimoles per liter on the problem statement over here. That's the ambient air. That's not the air in your lungs. Okay, so again, like this entire top part, this is all millimoles. Millimoles. Okay, this is the amount. Okay, and if you just look at units, let units be your guide. Liters, millimoles per liter. Liters are gone. Liters, millimoles per liter. Liters are gone. Liters, millimoles per liter. Liters are gone. Okay, the numerator is all just millimoles. The denominator, so now we've taken a breath. There was the air in my lungs when I first, between breaths, okay? Then I exhale, then I inhale. That is me taking one breath. So now my lungs are back to being full, and the full volume of my lungs is V. And this has units of liters. And now if you look at what just occurred, this is millimoles, this is liters. I have millimoles on top, liters on bottoms. I have just computed C sub t plus 1. Okay? So this is the process we've been doing. Now let's do some algebra. Okay, so what is this equal to? I'm going to factor out that C sub t. I have V minus W, C sub t, plus W beta. Okay, all of that is over V, which that's the same as saying I'm multiplying by 1 over V. Everything is over V. And maybe that'll help you know that we could just write this as V minus W times CT over V plus W times beta over V. Sweet. And now we need to do more algebra. We need to be more comfortable with algebra. So this is the same as V over V minus W over V times CT plus W over V times beta. Now V over V, that's 1. And W over V, what is this? This is your tidal volume. This is how many liters you exhale, which is the same as how many liters you inhale, which is not the same as the total volume of your lungs. This is lung volume. And this is the fraction of air in your lungs that you use in a breath, right? That you would exhale, that you would inhale. So in this problem, it's 0.4 over 3. That fraction is the fraction of air that's exhaled and inhaled, okay? And that fraction is given the name P. Okay, so the P that shows up in this problem, in this updating function, it's W divided by V, and that is how they get this updating function. Okay, so that's what's going on, and you are clearly expected to know this in the problem statement, because nowhere in the problem statement does it tell you that P is equal to W over V. It tells you W, and it tells you V, and then it just throws out this letter P. So we have to know this relationship. It's implied, okay? All right, fine. Whatever. So what this problem is now saying is that the concentration after another breath is 1 minus 0.4 over 3 times the concentration that's currently in your lungs plus 0.4 over 3 times the concentration of the outside air. Ooh, look at that. Nice. Okay, so 0.4 over 3, that's not going to simplify very well, so whatever, I'm just going to leave it alone. Let's run with it. Great. Now, you might think, okay, let me grab my calculator. No, stop, freeze, okay? Use Webwork. It's not so bad. So 1 minus 0.4 divided by 3 times, now I'm trying to compute C1. I'm trying to compute C1. So I had better use a C0, right? This subscript is 1 less than that subscript. That's all we're saying. So what's C0? This problem says it's 1. It's in that last little sentence. Plus, I guess I'm adding 0.4. You know, sometimes it's nice to cancel ahead of time, right? Make my life easier, okay? So this amount, this is C1, okay? Now, I could, if I wanted to, do 1 minus 0.4 divided by 3 And now, if I plug in C1, I'm going to get out C2, right? So I'm trying to compute C2. So let's plug in C1, okay? Copy, paste. There's C1. Looks gross. Don't sweat it. Plus 0.4. Okay, I've done the updating function now. You can see it works, right? But another option you could do is like literally just type this thing, hit submit. You now know the number is 1.2666 on forever, okay? And then that's what you could have put here. You could have put 1.266666 on forever, okay? Eventually Webwork won't care, and you could hit submit. Oh, look at that, they're both right. So let's do that play again. But now what we're submitting, sorry, this number here is no longer 1. God, I hate this formatting. There we go. It's the 1.4977. It's that thing up at the top left, okay? 1.497772. Sure, why not? Okay, let's hit submit again. Boop. All right, there we go. And let's do this again. And now this is 1 point, it was like 698069. Okay, 80, wait, yeah, 069. Probably won't care after that. Okay, so that's good enough. Submit. See, they're all working. Okay. All right. Now, what is the equilibrium value of this system? Now, we could, don't do this, okay? We could find the equilibrium by getting rid of the subscripts on the updating function. 1 minus p c plus p beta. And then we could find c. Okay, and remember, all of these actually have numbers, except for c. What I mean is this is 0.4 over 3. Whoop. Same with right here. Okay, this is 0.4 over 3. And wait a second, beta is 3. Those are gone. Okay, so this is actually just plus 0.4. Okay, so now it's much less scary, right? I just have a number in front of c and a number over here. Find c. Okay, what should you do? Well, you subtract c from both sides, and what that's going to do is make this side 0, and this minus c is going to kill that copy of 1. And so all that lives on is the negative 0.4 over 3c. And you know, while I'm at it, let's subtract the 0.4 over, okay? So now this is no longer 0. This is minus 0.4. And so then if we divide by this, so divided over, we have minus 0.4. You could write divided by minus 0.4 over 3, but division is the... Look, if I have a number and I divide it by 2, that's the same as that number times 1/2. What I'm trying to say when I tell you this is that if you ever get confused on like when do I flip and multiply, you've actually... There are cases where you do it and you don't even realize you're doing it. Division is always multiplying by the reciprocal. Okay, division is always multiplying by the reciprocal. So really, I'm multiplying by 3 over negative 0.4. And that's nice because I can see they cancel. Okay, I get that c is equal to 3. Okay, you could do it like this, algebraically. Don't. All right, let's think about the context of this problem. This beta equals 3 millimoles per liter. That is the air of the room that you're standing in. Okay, if you are locked in that room, and you take 1,000 breaths, I would say it's reasonable that the air in the room and the air in your lungs is basically the same, right? In fact, that's the point. This chemical in the room, its concentration in the room is eventually going to be the same as the concentration in your lungs. So you will always head towards beta or gamma, whatever they call the ambient air, okay? So, boop, there it is. Cool, done, next problem. All right. Yeah, this is silly, just get a fresh page. How many more problems do we have? We're on 8. All right, only a couple more. So, all right, weighted averages. You got 3 liters of water at 20 degrees Celsius, and you got 6 liters of water at 28, and then you pour them together, okay? Here's 9 liters of water, and this much of it was 20, and this much of it was 28. Okay, so then it equilibrizes. What a word, you know. And then we ask, what's the temperature? You know, what it do? All right. Well, here's the deal. How much of the 9 liters was 20? Oh, right. 3 of the 9 was 20. How much was 28? Oh, right. 6 of the 9 was 28. It turns out adding the fraction of each amount will give you the new total. Okay? So 3 divided by 9, famously 1/3, and that was 20. Stop it. 20 plus 6 divided by 9, also famously 2/3, and that's 28. Hit submit. There it is. Okay. That's called a weighted average. Whatever. All right. So here's an updating function, and s is 0.9 is the growth rate of species 1, and the growth rate of species 2 is 0.6. Damn, species 1 be having babies. Okay. And equilibrium p star equals 0 is okay. So then they're asking us like, what's going on with this? Okay. Now you could just guess and check it, right? Anytime you just have blanks and infinite, you have unlimited problem attempts. You guess and check. What do I want to say? P star, is it stable or unstable? I guess the nicest thing would be just graph this. And then you could just cobweb it. That's pretty much what we have at this point in time. This is in section, I believe, 1.9. It might be 1.10 if that exists, but I think it's 1.9 in this textbook. Yeah, let's go ahead and just graph it really quick. And maybe I can even sketch it by pen. Let's see. I don't know. So S is 0.9. I have 0.9 p sub t over, and I have 0.9 p sub t plus, and then R, which is 0.6, 1 minus p sub t. Okay? This is going to be p sub t plus 1. Okay, well, if I distribute this 0.6, then I have 0.9 pt over, and I'll have a 0.6 from this 0.6 times 1. I'll have 0.9 minus 0.6 pt, so that's just a 0.3 pt, okay? And let's see, this is a little bit tricky for my brain, so what I'm going to do to make it easier on my brain is factor out of the bottom of 0.3. So 0.3 would have to be multiplied by 2 to get 0.6, okay? And it would have to be multiplied by p sub t to get this. And now, if I look here, 0.9 divided by 0.3, that's the same thing as 3. So in fact, this updating function could be written like that. Sorry, t. Great. We could do more algebra, but you know what? Let's just go ahead and graph this. So, over here, let's get some DESI. There you go. Graphing calculator. And I believe I said 3x divided by 2 plus x. Okay, so here we are. And we're also going to care about the line y equals x. Now, look, well, we actually have, everywhere there's x, I could have done p sub t and then p sub t. And, but then it wants a slider. It doesn't like that, right? So I'm just going to do x, and we know that what I mean is the p sub t's. Okay, so now, okay, let's zoom in. So now you can see there's 2 equilibrium points. There's 0, 0, and there's 1, 1. Okay, this is the for beginning cobwebbing, you always sort of graph the y equals x line. It's just sort of given to us every time. And then there's the updating function. So now we could imagine cobwebbing on this. Okay, let's do it real quick. And we don't need any of that. Let's get rid of it. All right, so let's see what happens if I just start wherever I want to start. And I go updating function, y equals x, updating function, y equals x, updating function, y equals x. And you can see we're heading towards the equilibrium value of 1. The fact that we're heading this way means we're heading away from 0, okay? So that actually answers the question now. We know that we head towards 1 and we head away from 0. So if I go here, 0 is unstable. We head away from it. Unstable. And 1 was stable. We head towards it. Okay, submit. There you go. All right, so this is the same as the previous one. Remember how I did all that algebra? And Ugh, what the heck? There we go. And we ended up here, right? So notice how similar that is to this updating function. Okay, fine, whatever. Where is my, so select all equilibrium values. All right. So equilibrium values. Bap. Great. So we get rid of the subscripts. Okay, and we're trying to solve x is equal to x over a plus x. Okay, what do we do? First off, don't divide x. Okay, this was my warning from last time. X is a variable. If you want to divide a variable, you got to make sure it's not 0. What does that mean? Make sure it's not 0. Well, we should ask ourselves, is x equal 0? Could that happen? What happens? Plug it in. Plug it in. We get 0 is equal to 0 over a. Plus 0, but whatever. 0. Oh, you get something true. True. Which is a solution. X equals 0 is a solution to this, which means x equals 0 is one of the equilibrium values. Okay. Now also, if this is tricky, you could also just literally plug in like all of these. But so now we know x equals 0 is one of them. Okay. We can ignore this. I didn't read what that says. I don't really care right now. Okay. So, all right, now. So now x could be 0. But now we can say, okay, let's just assume it's not. Okay. Now if x is not 0, then you could divide. So now if I divide both sides by x, okay, then that becomes a 1, and this is a 1 over a plus x. But if you don't like that, you don't have to do it that way. Let's do it a different way, okay? And by the way, that start, you'd still have to solve for x. So let's do it a different way. Okay, so we're here. What should we do? Let's multiply the denominator over. So I have a plus x times x is equal to x. Okay, multiply it over. Really, I'm multiplying both sides by a plus x. And it just cancels on this side, and it appears on this side. Okay. All right, so now we should distribute. Great, I have x squared plus ax is equal to x. Now we should subtract x. X squared plus a minus 1 x is equal to 0. And now we factor in x. X 1 plus a minus 1 x is equal to 0. Okay, how can this happen? We have one number. We have one number and another number. And they are being multiplied to get 0, right? Okay, well, either this number is 0 or this number, 1 plus a minus 1 x is 0. Those are the two cases. X equals 0, we saw that before. That is one of the solutions. Here's the other one. If you solve for x, you'll get x is negative 1 over a minus 1, also known as 1 over 1 minus a. You sort of factor a negative 1 out of the top and bottom, and then those would cancel. But, okay, cool. So our two equilibrium values are 1 over 1 minus a and 0. Sweet. All right, 1 over 1 minus a and 0. What happens with this system if a is equal to 1? Well, let's see. Look, if you plug in 1, we have 1 divided by 0. Oh, shoot. 1 divided by 0? That doesn't seem very good. So my guess is that there's only one equilibrium. Okay, I'm just going to guess it and see if that's right. Why don't we like C and F? What happened here? Did I select all the equilibrium values where A is a positive parameter? Okay, I thought I did that. All right. Damn, I wish I hadn't deleted that. I mean, I know it's in my recently deleted, but let's just run through this again together. Okay. Select all equilibrium values. So we have x is x over a plus x, and I then have a plus x times x is x, and that's the same as x squared plus ax is x, and that's the same as x squared plus a minus 1x is 0. And then this is the same as x, 1 plus a minus 1x. That was my mistake. When I distribute, that would actually give me x squared plus a minus 1x squared. All right. So really, there's no x here. But there is an x here. Much better. Much better. Yeah, right? See, I hit that, I get x squared. I hit that, I get this. Okay? This is why, by the way, like I think it's, I don't know. I think our grading system needs to be reformed because even people getting a PhD in math, you know, you just go into this sort of like coasting thing and you just make these simple algebra errors, and it doesn't mean you don't know math. It just means you're human. And so if we don't allow exam redos, or, you know, it's just exams aren't great assessments, whatever. Okay, so if I factor out an x, this is an x plus a minus 1. That has to equal 0. Okay, same rant as last time. I have a number times another number, and they equal 0. So either this number is 0 or this number is 0. X plus a minus 1 is equal to 0. And if you solve for x, you have negative a minus 1, better known as 1 minus a. Haha, it's not C, it was B. Okay, great. Go away, come here, goodbye. Okay, so now why was this C still correct? Well, look at what happens if you plug in a equals 1. 1 minus 1, you get 0. And so 0 is the same as 0, so you don't have the 1. Okay, cool, that's it. See ya.